Okay, so we're going to take a look at a dollar. When we think about the concept of E, the idea is we're going to compound it over a year, and we're going to earn 100% interest. So essentially, like we're talking about, the dollar by the end of that year is going to double, right? But if I compound more and more and more throughout that year, we know that compound interest works in the sense that I actually earn interest on previous interest, right? So the more often I compound within that year, the more interest I'm able to earn on previous interest, okay? So let me ask you guys a very difficult mathematical question here. If I'm doubling my interest and I invest $1 and I only compound the interest once in a year, how much am I going to have at the end of that first year if I'm doubling my amount? $2. Good job. You guys passed. Everybody gets an A in the course. Okay, good. So if I only compound once a year, I only get $1 on that 100% growth because I had my initial $1 and now I get another $1 and now I have $2. And I didn't earn any interest on previous interest because I only compounded it once at the end of the year, right? Okay, so here, n equals 1 if I compound once a year. This guy right here is going to represent our $1 in this formula. This guy is going to represent 100% of the principal amount. So 100% of that $1. You may recognize this from previous compound interest questions that you've done in like grade 11. Okay, and then this guy is going to represent our interest rate. So in this case, our interest rate is 100%, so we're earning 100% on our $1. So moving the decimal over, we get 1. Now we have to divide it by the number of compounds per year. And that n is the same as the n in the exponent as well. Okay, because we're only looking at this over the period of a year. Normally, for this exponent, I would be multiplying number of compounds per year by number of years, but we're looking at this for 1 year, so we just get n times 1 for that exponent. Okay, so when we enter this into our formula here, we should expect to get out $2 from this. So we have 1 over 1, all to the exponent 1, and that gives us 1 times 2 to the 1, which is just 2. Okay, so as we suspected, if I get 100% interest and I just get it at the end of the year, I'm going to have double what I had before. I'll now have $2. Now, what our friend in the video that we watched was saying is that this doesn't quite make sense because these processes normally grow slowly over time. So rather than me taking $1 here and then all of a sudden at the end of a period I have the $1 I started with and then all of a sudden I have this new $1, we get this kind of like staircase of growth that happens, right? Rather than like our nice, smooth, gradual exponential curve that we like to kind of graph, right? So this doesn't quite make sense because how did I all of a sudden just get a new $1 at the end, right? So normally those things kind of grow slowly over time. So we're going to see what happens if we're continually compounding our interest, okay? So we're going to see what the limit approaches as we compound more and more often. Okay, so let's say now that we compound twice a year, so we get 50% the first time, 50% the second time, but after the first time I compound, I actually get a little bit of extra interest on top of my first compound. So we're going to enter in 2 for n. Okay, so we're going to do 1.5 to the exponent 2. Everybody needs some calculators out there. What do we get? We're going to round to 2 decimal. Actually, no, we won't. We'll round a little bit more. Yeah. 2.25. So now, if I compound twice a year, I have $2.25 at the end of that year. That's pretty good. So over the first little compound, I got a bit of extra money at that 6-month mark, and then at the end of the last set of 6 months, I had interest on that previous interest. Now, if I compound continuously, or I compound, let's say, 1,000,000 times in a year, I'm not going to have like an insane amount of money from starting from $1. Like there's no way that I'm going to get up to like $10,000 by the end of a year, no matter how many times I compound that interest. Agreed? So like the amount is going to go up if I compound more frequently, but eventually it's going to reach some kind of value that I can't really get any higher than. Even if I compound a bunch of times over the course of that year, I'm never going to get $10,000 if I just invest a single dollar. Agreed? Okay, so eventually these values, you're going to notice that they converge toward a particular value. So let's keep going here. Okay, so we're going to do 1.25 to the exponent 4. Okay, and I know we're dealing with dollars here, but we're just going to leave, like as we continue to go down the chart here, we're going to leave a good amount of decimals just so we can kind of see what's happening. Legend, can you take your headphone out, please? Legend, can you take your headphone out? Thank you. Okay, 1.25, yep.
How many decimals do you want?
Give me them all.
Okay, 2.44140625.
Okay, so we have about $2.44. I want to leave some decimals here just so we can kind of see, because eventually when we get down to some of the later columns here, we want to see those decimals. Okay, now let's see what happens if we compound 12 times a year, every month. Okay, everybody should be calculating. Get your calculator out if you don't have it out. What'd you get, Alexandra?
3.6, no, 2.61.
Is that what you got, Annika?
Yeah.
Okay, give me some more decimals though. 2.61 what?
Oh, I added. So 2.613.
03529.
Okay, great. All right, so we've got $2.61 about that if we compound 12 times a month. Now imagine if we did this every day. We're going to get a little bit of interest on top of our dollar every single day, and then each day that I get more and more of little pieces of interest, those little pieces of interest are also earning their own interest. That's the nature of compound interest, right? You get interest on anything that you put in, but also any previously earned interest. Okay. So we're going to calculate here 1 over 365 plus 1 to the exponent 365. Alexandra, what'd you get?
2.714567482.
Okay. So do you guys notice here the first little jump here I made about 25 cents? And it's starting to get a little bit less and less each time. So we're still obviously making more, but the jump here was like 19 cents more initially, and then this jump was even smaller. It's like 16 or 17 cents. Now I've made about 10 extra cents from the previous thing. So we can see that these are starting to converge toward a particular value here. Let's take a look at what if I got interest every second. Okay, this is going to be our new end value here. So we're going to calculate 1 over 31,536,000. Or sorry, 536,000, yeah. Jonathan, what'd you get?
I got 2.718281391.
1391, perfect. Okay, now of course we can never really figure out what this would be if I'm compounding my interest continuously, because that's kind of like infinitely compounding my interest. But suppose we choose like a really, really high number. In order to kind of see what these are converging toward, we're going to use the value 1 billion, so 9 zeros, and we're going to see what that would give us. Okay, so even if I compound my interest 1 billion times over a year, I'm still not going to get much higher than kind of where I'm at now. But I am going to converge toward a particular value. So let's enter this into our calculator. Jonathan.
I got 2.718281827.
Okay. This is the value of E. Okay? So this, as we look down this chart here, the limit as we approach infinite compounds of our dollar in this equation is actually approaching the value E. So we're going to make about $2.72 if I compound my interest infinite times over the course of the year. That's as high as I can get with continuous growth. So the interest is always earning interest on little bits of previous interest, but eventually it converges toward a value, and that value is E. So if I'm doing 100% growth, so doubling, the idea of doubling, we're going to converge eventually toward this idea of continuous growth, and that value converges, that it converges toward is E. So this is 100% continuous growth. Okay, so we're saying as our n gets higher and higher and higher, like we saw in our table over here, the idea is that we will converge toward this value E. So E is what we call an irrational number. Another example of something that is irrational that you guys have already used before is pi. So the idea of an irrational number is that it's unending and it's also unrepeating. So the difference between E and something like 1 over 3, for instance, is that 1 over 3 is non-terminating, but it is a repeating value, right? 1 over 3 is 0.33333333333 forever. So that's a repeating value. So I can actually express something like 1 over 3 as just 0.3, and we use this little bar, right, to show that it's repeating forever. But unfortunately with E, there's no like fraction that I can use to represent this because it's, and then there's also really no like finite exact decimal that I can use to represent this either. So have you guys ever like watched videos or like heard of anybody that like memorizes digits of pi? Okay. Well, they're out there, Claire. And what these people do is like, so pi is this idea of this non-terminating, but it's also a non-repeating value. So people are like, there's computers out there that are constantly generating like new digits of pi, and people have tried to memorize them before. But they're difficult to memorize because they're not repeating, right? So the pattern doesn't quite repeat. So that's the idea of E as well, is that it just infinitely goes forever, and then there's more and more numbers that are generated with this value. So irrational. Log base E. Yep, Alexandra? I will show you where E is on your calculator, yes. It will be different for all of you, so we'll have to take a look at that soon. Okay, so as you guys know, the difference between, oh, and by the way, to represent like continuous growth, sometimes we represent this as like an exponential function. So E as an exponential function would be this y equals e to the x idea. So as we know, Claire, what is the inverse of an exponential function? I'm asking you because this is on your video. We also talked about it.
Exponential function is...
What type of function?
It is an exponential function that is an inverse.
Okay.
I have no idea.
Chair? It's a non-exponential function. You're not wrong. Jonathan? It's a logarithmic. So exponential functions and logarithms, those are inverses of one another. So if we're going to talk about the idea of e to the exponent x, or growth by e, we should also talk about log base e of x, right? And this is actually a special logarithm. It's stored in our calculator. So we have two special logarithms that are in our calculator. One of them is log base 10. It's called the common logarithm. Log base e to the exponent x is stored in our calculator as this button. It's ln, or maybe I should say, known as the ln of x, and we write it as y equals ln x. So we say ln of x, or some people just say ln of x. Okay, and this is the natural logarithm. So we have the common logarithm and we have the natural logarithm. Okay, and of course this makes sense that this is the natural logarithm because e is 100% natural growth, right? This is kind of the idea of like things that grow slowly over time. So e represents natural growth, so the logarithm with base e is called the natural logarithm. So the idea is that many kind of naturally occurring phenomenon can be measured with base e exponential or logarithmic functions. And one other important thing to note is that if log base e of e is kind of similar to some of the logarithms that we've approached before, like what do I know about log base 2 of 2? What's any log to the base of itself? Equal to. Yeah, it's equal to 1. That's right. Because we're asking ourselves the question 2 to what exponent equals 2? Well, 2 raised to the exponent 1 is going to equal 2. So if I have log base e of e, you're going to see that as the ln of e because we use ln for log base of e. And that's actually equal to 1 because any logarithm to the base of itself is equal to 1. So if you guys ever see ln e, you can sub in 1 for that. Okay, so if you guys want, you can take a look and see if you can find the e button on your calculator. I'm going to pause the video for a second, take a look for that. All right, so we've all found our e value here. If you have any trouble finding your e value, if you're watching the video, you can always look online and I'm sure there's videos out there that can show you where your e button is and how to use it, and your ln button. Okay, so there's a couple little reminders for you guys here. These are our log rules because we're going to be doing a little bit of work with e and ln. So if I'm working with ln, one important thing to remember is that if I see ln, it looks a little bit different than what we're used to seeing, but ln is a logarithm. So all log rules apply if I'm working with ln. Okay, so I can use products become sums with lns because they're really just logs with base e. Okay, so we're going to do a little bit of evaluating on our calculator. I want everyone to, using that e button that you found, evaluate e to the exponent 3. We'll leave just like maybe 3 decimals. What did you get, Jeremy? So you should get 20.086 approximately. Okay, everyone just double check, make sure you can get that. Okay, now I want you guys to try, your ln button should be really close to wherever your e button is. I want to evaluate ln of 10 in our calculators. We'll round again to 3 decimal places. Alexandra, what'd you get?
2.303.
Perfect. And if we put in ln of e on our calculator, we should get 1. Yeah, that's right. Pardon?
Oh, it's just e to the 1, right?
Yeah, so if your calculator makes you input an exponent on there, then just do ln of e to the exponent 1. Yeah. Okay, now that we know how to evaluate those on our calculator, we're going to do some solving here. So we're going to refresh our memory on some of the log rules. So yesterday we refreshed our memory on some transformation stuff, exponentials, logarithms, and also polynomials. We're also going to refresh our memory on solving types of logarithmic equations, but this time they're going to be with e and ln. Okay, so in order to solve for some base to an exponent, remember e is a number, so the only unknown in this question is x. So we want to solve for x here. I need to get the base and the exponent isolated on one side. So we always start by getting the base and the exponent alone. That means I have 20 over 3 equals e to the x. And what do we normally do when we have an exponent that's an unknown? How do I get that exponent out of the unknown out of the exponent? Simran? So we usually log both sides, right? So I'm going to suggest, because we're dealing with e, can we use the natural logarithm? Can we ln both sides here? Yeah, it's like the same thing, logarithm of both sides. But I want to say we're going to do the ln of both sides here. Okay, and because ln is a logarithm, I'm still allowed to use logarithmic rules with this. And my power rule of logarithms tells me that I'm allowed to bring an exponent down when it's on top of a logarithm like that. So we're going to have the ln of 20 over 3, and that's going to be equal to x times the ln of e. Now the nice thing about using ln instead of logging both sides, which you can also do, you can definitely log both sides, but look what I have here now. Ln of e is 1, we figured that out, right? So if this equals 1, I know x is just equal to the ln of 20 over 3. Now certainly we can evaluate this, but it's in an exact form right now, which is nice. So we could actually just leave it in that. But we're going to also practice just entering this into our calculator. So if we were asked to round this, let's say to 3 decimals, what would we get? Yes, you would get about 1.897. Is that what you got as well, Alexandra?
Yeah.
Awesome. Okay, so this would be, if you're asked for an exact form, this would be more of like a rounded answer. So it depends what the question asks. Okay, so same deal as what we've done before, but instead of logging both sides, if you see that your equation has a base of e, you're going to ln both sides. Okay, someone want to take us on some thoughts on the next one? What would you do? Jonathan?
Well, you ln both sides like normal. You just got to make sure that the 1 and 2x, 1 minus 2x is group.
Okay. So you're saying this guy has to act as a group?
After you ln it, it goes to 1.
Right.
And
So
ln e equals 1, so you can just cancel that out entirely. So 1 minus 2x equals 155, and then you just isolate for x.
okay. So we're left with 1 minus 2x equals ln 55. We can bring over the 1. And we can divide out the negative 2. So we get x equals the ln of 55 minus 1 over negative 2. If I'm asked for an exact answer, that would be the answer I give. If I'm asked for an approximate answer, let's say rounded to 3 decimal places, what would we get here?
Did you take out the negatives on the negative 2 and negative 1? Or like
No, because the negative also applies to ln as well. So don't cross those out. What'd you get? Great. Okay, so this would be your exact answer here. This would be your rounded answer. Now, when we were working with logarithms, anytime I solved an expression like this, I could always actually plug it back into the original equation to check my work. Same deal here. So if I find x, I'm going to sub it right back in there, and I'm going to check that I get an answer that's like approximately equal to 55. Right? That's how I know that my answer is correct. So you can always sub back in to check, just like we did with logarithms. Okay, any questions so far? Great. Let's take a look at some logarithmic equations now. All right, any ideas as to what we can do for C, thinking back to our knowledge of logarithms? Okay, if I'm trying to isolate for a variable, I probably want to just start by getting those two things that are not inside the logarithm kind of on the other side here. So I'm going to move the 7 over and divide out the 2. We will get 10 over 2, which gives us the ln of x minus 3 equals 5. Okay, now I normally wouldn't write this line, but I just want you guys to remember that ln basically just represents the logarithm with base e. So how do we usually get something out of a logarithm if it's kind of like stuck inside and I'm trying to isolate for it? What technique do we use? That's still going to have something inside a logarithm though if I use change of base. Any ideas here?
You just rearrange the log.
How do we do that? Okay, rearrange into exponential form. What's the base? What's the exponent? The answer to the logarithm is always the exponent. So the 5 is the exponent, right? So it's e to the 5, and that will be equal to x minus 3. So we're changing this into exponential form. And I think that we can isolate now. It's just going to be e to the 5, and I'll move the 3 over, and I'll get plus 3. That's your exact value right there. Okay, can somebody tell me what this would be equal to if it were maybe rounded to 3 decimals? What was it, 1.1? Oh,
151.413.
awesome. Okay, and that's an approximate, so we'll just use our approximation. Okay, so if you're asked for exact, you'd give me something like this. If you're asked for rounded, you'll give us that. Okay, any thoughts as to how we can start part D for trying to find x?
The same trick as last time, because if there's nothing there,
Right.
if there's log e, then you can just do e squared equals 4 x.
Awesome. So we're switching this into exponential form.
And then, wouldn't it be best if we, what's called, divide the 4 to the other side and then do the rule again, like, what's called, like x log e equals log e squared over 4.
Okay, so you're suggesting we take the ln of both sides here?
Yeah.
Okay, and then we get to bring down the x. And we know that ln of e equals 1. So really this is just x equals the ln of e squared over 4. Okay, I could write this as my exact answer here. What would this be if I asked you to round to 3 decimal places?
So what is
6, 1, 3? Okay, did everybody else get this? Okay, double check, make sure you can get this on your own calculator. Okay, I think this actually rounds to 4, right? Because it's 3, 7. So if I'm rounding to 3 decimals, we'll round that up to 4. Okay. Now, what does the graph of e to the x look like and ln x? So remember, guys, we talked about how, pardon? Yeah, so it should look like a basic exponential and a logarithm. Now we're just using e. So let's just say maybe we'll take a look at a couple values here. Maybe we'll go from like -1 to 2. And we know any basic exponentials have a horizontal asymptote sitting at y equals 0. So I should not expect anything different if I have e to the x than if I had 2 to the x or 3 to the x. They all have horizontal asymptotes at y equals 0. Okay, we're going to plug each of these guys in and record our answers that we get so that we can figure out our y's here. So e to the -1. I got 0.367, so 0.37. E to the exponent 0, that's no different than anything else to the exponent 0. It's going to be 1. E to the 1, okay, this is just e itself, okay? So if we're definitely going to round it, but if we're rounding it, it's about 2.72. Okay, and then e to the exponent 2, we'll get about 7.389. So yeah, I guess we'll just write that as 7.39. Okay, so let's graph that guy. Start there. All right, so there's y equals e to the x. I'm just realizing that I did this one in blue, and I probably should have done it in red because this was labeled in red, but oh well, we'll switch it around. Okay, and if ln of x is the inverse of e to the x, how do I get the points for ln of x? What's a quick way I can do that? Simran? Flip them. So we'll get just the reverse of what we have on the left here. And if you guys remember from yesterday, we talked about our horizontal asymptote will become a vertical asymptote at x equals 0.
Wait, is it the 0 and 1 switched, or?
Oh, yes, sorry. I was just testing you guys. You passed, Claire, good job.
I did that too, that's the only reason I know.
Okay, so let's just pencil in our vertical asymptote here. We'll label that as x equals 0. And then we'll graph our points here. You're right. Let's just extend it a little bit. We'll extend it to 7 and 8. And that's at 2. Okay, and remember that our graphs should be, if they're inverses of one another, they should be reflected over the line y equals x. So this should make sense that we have kind of this line y equals x as our line of reflection. So imagine if you turned this kind of diagonally and folded it over that green line that I just penciled in. You should have two mirrored functions on either side. So these look very similar to our regular exponential and logarithmic equations. They just have bases of e. And as we learned about yesterday, we can do transformations to any exponential function and any logarithmic function. So you're going to perform transformations to e to the x and ln to the x, or ln of x, similar to how you would perform transformations to our functions from yesterday. Okay? If you want to use kind of like the base level key points, this would be 1, 2, and 3. And then you'd use 1, 2, and 3 if you're doing transformations. Or you can use the whole set of points. It's up to you, however many you feel that you need. Okay.